Hello everyone, I'm Hanan Bashir. I'm currently pursuing chemistry from IIT Bombay. Today we are going to see lecture 6 uh, on bonding of the course CH104 in organic chemistry. So let's start. So chemical bonding will have these energies which you can just see through. Covalent bonding, when two atoms will have a similar electronegativity, they will do covalent bonding. But if they have large difference, then it is ionic bonding. Then there are type non-polar and polar covalent bond. Lewis, Lewis has enabled us to study the acid-base theory and the Lewis structures, which we have seen before. Then he proposed the theory of bonding also. Skeletal structures, how to draw skeletal structures. So we'll just take a molecule, plot its atoms over space, and then we'll make bonds between them by observing which atoms will share what a number of electrons with each other. So it is just counting. Then this is the method how we will draw. So if we have two or three atoms in space, then we will draw double dots or a solid line to link any of them with each other. So you can see that placing electrons around atoms. So first, how will we start? So ClO2 minus. So we'll just see this example. So OClO will make them in space. Cl is the central atom. 7 electrons on chlorine, valence electrons, 6 on oxygen, and one extra because of this minus, which is 20. Then deducting 4 for 2 here and 2 here for bonding between them. Then completing the octet on the peripheral atom first before the central atom. So we'll get 16 minus 12 equal to 4 because we'll add all these lone pairs on oxygen, and afterwards rest will be the lone pairs on the central atom, which will give us this. Now, do we need to create multiple bonds? No need, because there will be only sigma bonds in this case, and this is the final structure. Similarly, you can do this carbon monoxide, but in the final structure, we will have to make the oxygen donate his lone pairs towards carbon because this is a DT bond. Then resonance structure. So resonance structure is a structure which is used to represent those molecules which cannot be represented by the classical Lewis structure and which does not match with the experimental observations. So bond length of HCO2 minus, actually CO3 minus also as well, was predicted by Lewis structure incorrectly because we could see that there is resonance here and hence it should be shorter as compared to the normal one, and they should be both equal. So resonance means bond flips back and forth as in both cases. The number of molecules with odd number of electrons exist, so no octet. So this is nitrogen oxide which will have odd number of electron, and you can see this is because it cannot complete its octet. Then BF3 as well, and a central atom will have more than electron, which is SF6. So these are the cases when the octet rule is not obeyed, and O2 is paramagnetic. And geometric and shapes of the molecule, we have no information about them. WACPR theory, or VACPR theory as we say, is based on the idea of electrostatic repulsion of the atom. So we will adjust them in space accordingly that the repulsion is minimized. The lone pairs will have maximum repulsion between each other, whereas bond pairs will have minimum, and lone pair bond pair will have intermediate repulsion. So more bond angle will be between lone pairs, and lesser will be in lone pair bond pair, and even less in the bond pair case. Then predicting molecular geometries. So how do we do that? We draw the Lewis structure and then we arrange them in a spherical space such that the repulsion between the atoms are least or the distance between are the maximized. Then molecular shapes. These are the definition: bond distance and bond angle, as you know already. Then AX2, AX3, these are the number of atoms which are at the periphery, and this is a steric number 2, 3, 4, 5, 6. So accordingly, we will get these structures: linear, triangular, planar, tetrahedral, trigonal, bipyramidal, and octahedral. And this is again done with using the lone pairs into consideration. Similarly, we have done that again. You can keep these examples in mind as they could be asked in the exam. But we can easily predict them as we know how to draw the Lewis structures. Now, although WCPR theory is successful in predicting the molecular geometries of main group, but it fails to predict shapes and isoelectronic species and also transition metal compound because they have some different properties as well. And WCPR cannot apply to heavy deep block compounds, and it can also be considered for this where the relative size of substituent and stereochemical inactive lone pairs are different. Then valence bond theory uses the concept of hybridization of atomic orbital to prior to the bond formation. So this is the more useful theory because it matches with our observations as well. So you have to hybridize atoms in this case. So we get sp, sp2, sp3, sp3d, sp3d2, as well as the front ones also, the dsp2 and d2sp3. Then these are the all the structure which correspond to these hybridized orbitals, and these are the examples which you have to keep in mind. This is s orbital, p orbital, and this is the orientation of p along different axes. So we get this pz, px, py, and these are for the d orbitals. This is WCPR theory, and this is BBT theory. You see there are the hybridized orbitals here, and these are unhybridized ones. Here, this is the bonding between H2. So this is hydrogen fluoride, and this is F2. Then valence bond theory will help us to determine the geometry in 3D space. So this is 180 degree if it is BeCl2 because we'll get only sp. So sp will always have 180-degree conformation in space. And valence bond theory, here this is beryllium. So we see that there are two electron in 2H2, and on mixing we get sp. Then afterwards we make the bond with chlorine, so we get BeCl2, and overlapping we get 180 degrees. Then this is the structure for BF3. We do the same and we get the structure. Similarly for H2O, there will be total four steric number. Uh, and you see that the sp3 are taking the hybridization of lone pair into account as well. The sp3 hybridized orbitals, in the case of CH4, then ethylene will have this pi over bonding as well, but we take into this sigma bonds into consideration only. So we get sp3, and in this case we will get sp. Sorry, in this case we get sp2. PCl5. PCl5 will have the trigonal bipyramidal geometry because after we mix we get sp3d structure. This will have this shape. And SF6, which will have an octahedral structure in space, we can hybridize it by mixing these electrons. Then you see, if you have question like uh, describe the bonds and orbitals in acetone. So if we create the structure as follows, then we can observe that the oxygen will also have sp2, sp2, and sp2, and carbons will have here sp2, sp2, and this will have sp3. Now, Bend's rule. What is Bend's rule? So, most electronegative atom prefer hybrid orbital having less s character, and more electropositive will have the more s character preference. So, how do I keep it in mind that if it is preferring s character, so this electropositivity has to be kept in mind, whereas electronegative, then it will should have less s character preferred. The bond angle in CH4, CF4, and CH2. This can be described by this Bend's rule that hydrogen, since it is less electronegative, will prefer the orbital which have more positive S character. Similarly, in case of F, it will have preference of the orbitals which have less S character. And this will describe the bond angle as well. Since fluorine is more electronegative, it pulls the electrons towards it, and hence the electrons are far, so hence there will be lesser repulsion. But if they are closer to the phosphorus, then we see that there is more repulsion, so chlorine will have more bond angle. So this is a structure which will help us to keep this in mind. So if electrons are nearer, then there will be more repulsion, hence bigger angle. And which of H2 and F2 will have larger XOX bond? So we know that fluorine is more electronegative, it pulls, and since it is farther the electrons, we will get a shorter bond angle in case of F2, and H2 will have a larger bond angle. So this is our answer. And but WB theory does not describe the color of compound spectral properties and does not explain the magnetic properties as well. So WBT gives emphasis of localized bonding model. So here we end the lecture 6. Thanks for watching.